Okay, this is part 2 of the lecture for Tuesday, March 15th, talking about graph theory. So if you haven't seen part 1 and you're watching these out of order, you might be a little confused. Strongly suggest you go start with that one. So I want to talk about some graph terminology and maybe also some problems related to graphs. So if x and y are two vertices in some graph G, and there's an edge that contains those two vertices. So this is a set that's inside of another set, because remember, edges are subsets with two things in them. Then x and y are adjacent. So we use the word adjacent to talk about two vertices that have an edge between them. We do not say that they are connected. Connected is maybe a natural term that you might want to use from an English perspective, but we're going to use connected to mean something very specific later on. And it's not going to mean this, so we want to avoid saying that x is connected to y just because there's an edge from x to y. That's not what we mean. So x and y are adjacent. We also say that x and y are the endpoints of the edge, and that x and y are incident to the edge. So if we're focusing on the relationship between x and y, we call them adjacent. If we're talking about the relationship between x and the edge, or y and the edge, we call them endpoints, and we say that they are incident. Okay. So now I want to define the neighborhood of a vertex. So in a graph G, the neighborhood of some vertex x is, we use this notation, n little g of x is defined to be the set of any vertex y that is adjacent to x. So there is an edge x comma y. Okay, so just as a quick example, if this is my vertex x and I have some graph, oops, add those as well. This graph might look familiar. The neighborhood of x are all the vertices where there's an edge adjacent, incident to x and that other vertex. So this is in the neighborhood, this is in the neighborhood, this is in the neighborhood, this one, and this one. Then I have three vertices that are not in the neighborhood of x. Those three vertices are not in the neighborhood of x. And then I also have x itself. So question for you, is x in the neighborhood of x? Is there an edge that contains x and itself? And the answer is no. Which makes neighborhood, in my opinion, not the best word to describe what's going on, but it is true that there's no edge from x to itself, so x is not in its own neighborhood. you might come across a term closed neighborhood. A closed neighborhood is a neighborhood of a vertex plus itself, union itself. But in general, when we talk about neighborhoods, we don't mean the vertex itself. It's this bubble around X that doesn't contain X, but contains everything X is adjacent to, but you don't go out further than that. Okay, that's our neighborhood. So, one more definition, and then we can start asking interesting questions. The degree of a vertex is the number of edges incident to that vertex. If we're talking about a simple graph, then every edge incident to a vertex goes to another vertex. And so in a simple graph, the degree of X, which we typically write deg of X, is equal to the size of the neighborhood of X. By the way, I've dropped the little g here because I didn't name the graph. That's okay. If it's clear what graph you're talking about, then we don't always write that little g. If there's multiple graphs going on, which there might be in a moment, then we can also talk about degree in g of X and neighborhood in g of X, like that. If we don't have a simple graph, if we have a multi-graph or if we have loops, this might not be true. There might be more edges incident to X than there are neighbors of X. So not necessarily true. In multi-graphs or graphs with loops. Typically, if we have a graph with loops, we would count a loop as adding 2 edges to the degree because both sides of the edge are incident. So typically loops would add 2 to the degree. So just as an example, we can look at the same graph again. And talk about the degrees of each vertex. So this vertex has degree 1. This one has degree 1, 2, 3, 4. Degree 3, degree 3, 1, 2, 3, 4, 5, 6. Degree 3, degree 3, degree 4, degree 1, and degree 0. So we've got all of those degrees. Then the other thing I want to note is that in a directed graph, we can also talk about how many edges are incident pointing away from the vertex and pointing towards the vertex. So we also talk about in degree, which we write degree minus of X. In degree is the number of edges pointing towards X. And out degree, which we write degree plus of X, which is the number of edges pointing away. From X. So if I came back to this graph and added edges, or added orientations to all of these edges, and I'm just sort of doing this at random, just directing all of these to get something interesting. This one needs a direction as well. Then I could talk about in degree and out degree. So the this vertex has in degree 0 and out degree 1. And if we look at this vertex, it has 1, 2, 3, 4, 5 vertices coming in. So in degree 5 and out degree 1. And so if you add up your in degree and your out degree, you should get your degree, because every vertex in an oriented graph, every edge in an oriented graph has some orientation in or out. If you had a digraph, directed graph with loops, then your loop would count once for in degree and once for out degree. Okay, enough definitions. I want to talk about some interesting questions. So, question, is it possible that every vertex in a graph has a different degree? Okay, so think about that for a second. So what do we do when we get a problem like this? First thing we should do is we should try drawing some examples, especially for graphs. Right? Let's see if we can come up with one. So here's 3 vertices. Right now everybody has degree 0. That's no good. So if I add this, then I have 0, 1, and 1. The ones still have the same degree. So I might do this. But then I have 2 and 1. That's good. They're different. But now this one has degree 1. So that's a bummer. But if I add this edge, then everything will have degree 2 again. So I need something else. So maybe I'll add another vertex. And now I've got 1, 2, 2, and 1. Let me add another edge here. So now I have 1, 2, 3, but then I have 2 again. And it seems like I could go with this for a while, but it seems like I'm always close, but I can never quite get there. So we might try and think about why this is. So if I have a graph on n vertices, what are my options for degrees? Since a vertex can't be adjacent to itself, at most it's adjacent to everything else. So in this example, this vertex is adjacent to every other vertex in the graph, which means my biggest degree possible is n minus 1. My smallest degree possible is 0. So I can have degree 0, degree 1, degree 2, all the way up to n minus 2, n minus 1. I have n different options for degrees here. I've listed out n different numbers. So at first it looks like, okay, maybe it is possible, just have one vertex of each degree. Except is it possible to have a vertex of degree 0 and a vertex of degree n minus 1 at the same time? What would that mean? A vertex of degree 0, we say, is isolated. Vertex degree 0 is isolated. If you have an isolated vertex that's not adjacent to anything, you can't also have a vertex of degree n minus 1. Because a vertex of degree n minus 1 has to be adjacent to everybody else in the graph. But a vertex of degree 0 is not adjacent to anyone in the graph. So you can't have somebody adjacent to nobody and somebody adjacent to everybody at the same time. So we can't have both of these in our graph. Which means if we line up all of our different options, we could have 1, 2, 3, blah, 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 up to n minus 2, and then we can either have n minus 1 or 0, but not both. So now I have n minus 1 different categories and n different vertices. Some category has to have at least 2 vertices in it. I can't spread my vertices out so that they're all in a different category. So is it possible that every vertex in a graph has a different degree? No, not possible. Well, kind of. Because I am lying to you. It is possible. There's one example. There's exactly one graph where every vertex has a different degree. And that is if you're just a single vertex. So that is the graph whose vertex set has one element. I'll just call it V, and whose edge set is the empty set. I have one vertex, I have no edges. Might look like this. That vertex has degree 1, and that's the only, has degree 0, and that's the only vertex. So every vertex has a different degree. This is a very silly example. As soon as you have at least 2 vertices, it's not possible that every vertex has a different degree. This is why I really like graph theory. We've only been talking about graph theory for 40 minutes, not even, and we've already come across a question that wasn't immediately obvious, but the answer is really nice. It's easy enough to explain the question and the answer. So graph theory is actually where I do a lot of my research. It's one of my favorite fields of mathematics, so really looking forward to this section. Okay, let's ask another question. Is it possible for every vertex to have the same degree? Sort of the opposite of the last question. And so again, we might approach this by trying to draw some pictures. And if I draw this picture, I'm already done. Every vertex has degree 0. I did it. Okay, maybe that's a silly example. Can I make them all have degree greater than 0? Yeah, these all have degree 2. That's also possible. I can even get a really funky looking graph going on. There we go. If you check out this graph carefully, every vertex has degree 3. So here I have 10 vertices. but every vertex has degree 3. This is 3 vertices, every vertex has degree 2. This is 3 vertices, every vertex has degree 0. So these are called K-regular graphs. A K-regular graph is a graph in which every vertex has degree K. A couple more things to talk about in this part. So if we look at a graph, we can ask, what is the smallest degree out of any vertex in this graph? That's called the minimum degree, and we denote it with a lowercase delta. So lowercase delta of G is the minimum degree. Try that word again. Minimum degree of G, which is the smallest degree among all vertices of G. And we also have capital delta of G is the maximum degree. That's the largest degree amongst all vertices of G. So if we go back to this graph from before, our minimum degree is 0. That's our smallest one. Our maximum degree is 6. And if I got rid of this vertex, then my minimum degree would be 1. I have 2 vertices that both have degree 1. That would be my minimum. Okay. Next, I want to talk about something called the handshaking lemma. The handshaking lemma says if I add up the degrees of all of my vertices in my graph, and the way we write that is using our sigma notation. Now, normally when I use sigma notation, I would write I equals start to end. And that would mean do I equals start plus 1, I equals start plus 2. But there's no good way to list out my vertices. So instead, I'm going to write sigma vertex in V. So this means loop over every vertex in my set V, or maybe even V of G. And this just means add it up for everything that you find. So I'm going to add up the degree of V for every vertex I have. And I claim that that's going to be equal to twice the number of edges of G. Okay. So let's prove that. I'm going to do a combinatorial proof. So I'm going to count something 2 different ways. One way with this side and one way with this side. And the thing that ends up working in this case is I'm going to count the vertices in my graph as they are endpoints. So count the endpoints of my graph. So method 1, each vertex is an endpoint for each edge it's incident to. Right? remember what an endpoint is. If you have an edge, the two vertices that make up that edge are the endpoints. So if I look at a particular vertex, it is an endpoint of any edge that it's a part of. So each vertex is an endpoint. And how many times is my vertex incident to an edge? Well, that's exactly its degree. Each vertex is an endpoint once for every edge it is adjacent to, which is degree of x many. So by the rule of sum, I break into cases depending on which vertex I'm looking on. By rule of sum, there are sum across all of my different vertices, degree of v endpoints. Okay, that's giving me this side. So now method 2, I need to come up with a way to count endpoints that's going to give me this quantity. And this side actually ends up being significantly easier. I'm supposed to get twice the number of edges. Well, how many endpoints are there for each edge? Each edge is incident to two vertices. Those two vertices are the endpoints. So each edge is incident to two endpoints. So there are 2 times the number of edges, many endpoints. Okay, and now I just need to wrap this up. Some nice conclusion. Since the sum across my vertices of the degree of my vertex and twice the number of edges both count the number of endpoints in my graph, sum across all of my vertices, degree of v is equal to twice the number of edges. Edges of G, which was my original lemma. So this is a case where doing things with a combinatorial proof is crucial. Right? There's no algebraic way to prove this lemma without knowing about the graph. We really did need this combinatorial argument. Why is this called the handshaking lemma, by the way? A classic way of proving this lemma is to say that there are n gentlemen in a room, and each gentleman shakes another gentleman's hand some number of times, and you want to know how many, you want to say that twice the number of handshakes is equal to the sum of how many times each gentleman shook someone's hand, because every handshake has 2 people shaking a hand. So if we add up all the handshakes per gentleman, we get twice the number of total handshakes. So I want to use the handshake lemma to talk a little bit more about k-regular graphs. That'll be the last thing in part 2. Question: is there a 3-regular graph on 7 vertices? So I want to find a graph where there are 7 vertices and every vertex has degree 3. Now again, it's a relatively easy to state problem. Let's try and do it. Here's my first vertex. It has to have 3 neighbors. And now I've got to worry about some cases, because this guy could maybe be adjacent to some of these or maybe not. Just for the sake of trying things, let's say it's adjacent here, but I make a new vertex here. And now this guy needs 2 more vertices. I already have 1, 2, 3, 4, 5, so I only get 2 more vertices to work with. Let's make 2 more vertices, and let's make that happen. So this guy's good, this guy's good, this guy's good. This one needs 1 more edge, so I'll just add it there. Now that one has degree 3. This one gets 1 more edge, so I'll add it in there. Now that guy has degree 3. This guy needs 1 more vertex. Now he has degree 3, except this guy only has degree 2. And anywhere I add it, I'm going to push somebody too high. I'm going to push the vertex up to degree 4. So this didn't work. So maybe I go back to my original blue picture and I try again, and I try something different, but nothing's going to end up working. And the handshaking lemma can tell us why. So is this possible? No. And I can prove it by contradiction. So assume, for sake of contradiction, that there is such a graph. I want to use the handshaking lemma. So the handshaking lemma says that if I add up the degree of every vertex, I'm supposed to get twice the number of edges. Well, this is a 3 regular graph. So every vertex has degree 3, and there are 7 vertices. So I'm adding up 3 for every vertex in the graph. That means I'm adding up 3 7 times. So that tells me that 7 times 3, which is 21, is supposed to be twice the number of edges. And now I've reached my contradiction, because this has to be an even number. The number of edges has to be an integer. But 21 is an odd number. So I've reached my contradiction. So it is not possible to draw a 3 regular graph on 7 vertices. The handshaking lemma says you would have to have 10.5 edges, and that's not possible. Right? You could see if you could have 10.5 edges, if you could have a half edge here, where this starts at this vertex and then doesn't go anywhere, just goes off, then it would be possible, but there's no way to have half an edge, so there's no way to make this happen. So we asked, is it possible for every vertex to have the same degree? And we said, yes, k regular graphs are possible. But this clearly shows they're not always possible. If your number of vertices n is odd, and your regularity k is also odd, then the handshaking lemma says it's not possible. So here's a challenge for you. If n is even, or if k is even, or both, can you find a k regular graph on n vertices? So that's a challenge. Not going to answer it here, but a good thing to think about. That brings us to the end of part 2. This part's a little bit longer. Then we'll go into part 3. Part 3 is a little bit shorter again, and that'll be the end of the lesson.